Welcome back to Math 104. We are considering the experiment of rolling a fair die 6 times, and we're thinking of this experiment as having 6 people participating, each one rolling their own fair die. We ask, what is the probability that each person obtains a different number? We have here an experiment with equally likely outcomes. That means that the probability of this event will equal the number of ways the event can occur, that is, the number of outcomes in the event, divided by the total number of different possible outcomes for the experiment. Now, the total number of different outcomes for the experiment, we have already computed. That was 6 times 6 times 6 times 6 times 6 times 6. That is to say, that there is, for each person participating in the game, a slot that is a stage in the experiment. Forming an outcome here is a 6-stage process. Well, if that's true in the denominator, where we're understanding just how many different possible outcomes there are, it's also true in the numerator. The question is, how many ways are there to carry out this 6-stage process such that this event occurs? Well, what contributes towards this event occurring? The first person rolls and can obtain any number. We are still on our way towards our event occurring. Whatever number the first person rolls, the second person must roll a different number. Notice that we can call the people person 1, person 2, etc. Even if they roll simultaneously, it's still the case that whatever person number 1 rolls, person number 2 must roll something different in order for our event to occur. And whatever person number 1 and person number 2 have rolled, person 3 must roll something different. There are only 4 numbers that person 3 could roll, such that the outcome belongs to this event. That leaves 3 available numbers for person 4 to roll, 2 available numbers for person 5 to roll, and after the first 5 people have already rolled their dice and obtained different numbers, there's only 1 number that person 6 can possibly roll, such that our event is occurring. We have counted in the numerator the number of outcomes in our event, and we have counted in the denominator the total number of outcomes possible for the experiment. It turns out that this equals 0.0154 approximately, and that is quite a low probability. What's interesting about how low it is that if you think back to what an ideal data set is for the experiment of rolling a fair die, it's to obtain a 1, a 2, a 3, a 4, a 5, and a 6 on 6 rolls of a fair die. That's exactly this event, which we've just figured out, is quite improbable. No one's saying that you are likely to obtain an ideal data set when you perform this experiment. The reason we talked about ideal data sets was something different. So we've computed this probability. We move on now to the probability of the other event, that there is a match. In other words, that at least 2 people roll the same number. The key is to understand how these events are related to one another, and in particular, they are complementary events to one another. They are complementary because either one happens or the other happens. When the experiment is performed, either everyone obtains a different number, or it is not the case that everyone obtains a different number. To say that the numbers are not all distinct from one another is the same as saying that there is a match, that there is some pair of people, at least a pair of people, who have the same number. Thus, the probability of our second event is just 1 minus the probability of the first event, and that is approximately 0.9846. This expression, 6 times 5 times 4 times 3 times 2 times 1, in other words, starting with the number 6 and multiplying by successively smaller whole numbers until you reach 1, has special notation and terminology. It is written as a 6 with an exclamation point, and it is read 6 factorial. It does not say 6, but 6 factorial. In general, we can do this for any number. For example, 52 factorial equals 52 times 51 times 50 times 49, etc., all the way down to 3 times 2 times 1. Do you really need to write the 1? It's traditional. So this is 52 factorial. We can do this for any number. And we've seen that 6 factorial was relevant. It showed up as the numerator in a certain probability computation. Now, given that there are 52 cards in a standard deck of playing cards, can you think of a concrete interpretation of the meaning of 52 factorial? Not 52! but 52 factorial. So here's one interpretation. Consider the experiment of having 52 people, each with his or her own deck of playing cards. This is analogous to the 6 dice, one for each of 6 people. Just as we had each person roll their own die, now we're going to have each player draw one card from their own deck. If that's the experiment, then 52 factorial is the number of outcomes in the event everyone picks a different card from everyone else. Just as 6 factorial was the number of outcomes in the event everyone obtains a different number on their die, similarly here, 52 factorial counts the number of ways that all 52 people could possibly obtain different cards from everyone else. Here's another interpretation. 52 factorial is the number of different ways in which a standard deck of cards can be put in order. That is, the number of different results of shuffling a deck of cards. When you shuffle a deck of cards, you produce a certain ordering of the deck. Forming an outcome is really a 52-stage process. There's card number 1, 52 possibilities for what that could be. Then there's card number 2, 51 possibilities for what that could be. Then there's card number 3 after you've shuffled. There are 50 possibilities for what that could be in light of the cards that have already been put in place, etc., all the way down. So this is indeed 52 factorial. How much is 52 factorial? It is vast. It is approximately 8 times 10 to the 67. That means write down an 8 and then 67 zeros after it. That is quite a large number of zeros. To put it in perspective, this is only slightly less than the estimated number of atoms in our galaxy. What's a practical consequence? Well, one practical consequence is you might have thought that in one weekend at Atlantic City or a year in Atlantic City, they must go through all possible shufflings of a deck, don't they? But actually, no, they come nowhere close. Of all the different possible shufflings of a deck of cards, most of them have never been achieved. That's how vastly many there are. That's amazing when you think about it. Go out and tell that to someone today. This brings us to the famous birthday problem. If there are 3 people in a room, what is the probability that they all have different birthdays? We saw earlier how the outcomes can be thought of as words of a certain kind in a 365-letter alphabet. We're going to pretend that there is no such thing as leap year for purposes of this problem. We are also going to assume that each day on the calendar is equally likely to be someone's birthday as any other day on the calendar. In the experiment as a whole, there are 365 times 365 times 365 different possible outcomes. How many count towards our event? 365 times 364 times 363. 3 slots here for the number of people in the room, and 365 possibilities initially in each slot. What then is the probability that there is a shared birthday among them? What is the probability that they do not all have different birthdays? This is just the probability of the complementary event. This turns out to be rather a small number, only about 0.0082, so it is quite unlikely in a group of 3 people that there is a shared birthday among them. Now what about 20 people? What is the probability that they all have different birthdays? So this is going to be 365 times 365, etc. I won't write them all out, but I will indicate that there are 20 of them. In the numerator, we have 365 times 364, etc. Let's be careful and think about what the last number here needs to be, such that there are 20 numbers listed descending. The last number should not be 345, but rather 346. Think of it this way. There should be 20 numbers in this numerator if we write them all out. What does that say about the last digits of those 20 numbers? Well, 2 of those 20 numbers should have a last digit of 5. 2 of those 20 numbers should have a last digit of 4. 2 should have a last digit of 3, etc. But if there were a 345 here, in the middle there would be a 355, and in front there would be a 365. That would give us 3 numbers with 5 as the last digit. That's 1 too many. If you still don't believe me, I suggest that you write out these numbers and discover that from 346 through 365 there really are exactly 20 numbers. So what is the probability that there is a shared birthday among them? It should be 1 minus this, and that is actually not such a small number. It's approximately 0.4114. With only 20 people in the room, there is a better than 40% chance of a shared birthday. That's surprising, but it does follow from our computation. It turns out that with 23 people in the room, we cross a certain threshold. With 23 people in the room, there is a slightly less than 0.5 probability of no shared birthday among them, and therefore a slightly greater than 0.5 probability that there is a shared birthday among them. This means that with 23 people in the room, it is more likely that there will be a shared birthday than that there won't be. If this is true for 23 people in the room, it is certainly true for more than 23 people in the room. Before going on to the next video, compute the probability that with 8 people in the room, if each one randomly picks a whole number from 1 to 50, there is a shared number among them. Think about how this picking a number problem is related to the other problems we've just looked at. And then, which is more likely, that there is a shared number among them or that there is not?